Just to be clear, these are just like preliminary notes for a person who's not supposed to even know much about physics, but just be able to study the historical developments and its implications. Hi, my name is Wani, and I'm a philosophy student at La Sorbonne, and I thought I'd share with you my actual exam notes for my finals on the philosophy of physics. So I thought that this video would be an introduction to the nature of light, so the two theories of light as either being corpuscular or a wave. I thought that I would just, make a video that I thought would have been helpful for a person like me who wanted to know what quantum mechanics was about. I just wanted something where it's just like, okay, so tell me what's happening without making it sound extremely complicated, but also don't dumb it down because, trust that I can actually piece a few things together. But without further ado, let's just begin. So what is the nature of light and how did this lead to the birth of quantum mechanics? So in 1815, there was competition between two theories of light, whether it was corpuscular or a wave. So in the 19th century, Young had this experience called les expériences d'interférence. In English, it's double slit experiment. I'll put like a photo of it somewhere. If you've ever been introduced to quantum mechanics, someone usually does is show you like a screen with like a wave and you're just like, I don't understand how any of this makes sense, but I will try to explain this to you. So the whole point of this experiment by Young is to show that light behaves like a wave. The difficult thing about quantum mechanics is that you have an aspect that it's easier to explain when you actually have other aspects explained as well. So there are two things to take into account when you think about interference and what it has to do with the wave. The first is interference, and the second is diffraction. So interference is the idea that two electrons or two particles will interfere with each other. They will basically move each other. How I understand this is that with classical mechanics, there's this idea or there's this myth, and I refer you to Schrödinger's Science and Humanism, where he talks about the illusion of the perfect picture. The idea before was that you should be able to tell exactly where a particle is at any time, at any given moment, but the indeterminism of quantum mechanics comes into account of how it is that no, we can't actually tell exactly where the particle is. I hope to elaborate this in the other videos, but when we say indeterminism, there is the indetermination of the particle and the indetermination of its evolution. And based on which part it is that we don't actually have the exact answer, the exact response, is how it is that you end up with the two interpretations, the two massive divisions of the indeterministic model of a complete picture, which is the Copenhagen interpretation, or you have the other side, which is Einstein and Bohm and Schrödinger's interpretation, which is a deterministic model with an incomplete picture. I'll go into that in the other video. But getting back to this, the idea is with interference, once you can, and this comes from Bohm with the pilot wave, but basically it's saying that there are two slits. If the particle does not move like a wave, when you shoot light through it, the particles should hit just straight through the slits. So then you should only have two marks. But what we have is that we have like the darker parts and we have lighter parts. So the idea is that some particles, they go through the slit and then they move and they interact with one another, and then they hit the screen in that way, and that's why you have a variation of color and not just two dark lines. The other thing to take into account with this was diffraction. So the definition is when waves spread out and create when it passes through an opening or around an obstacle, which is what I explained to you. So interference is how they interfere with one another. Diffraction is how it is that we can see how it moves around an obstacle. There are two types of interference, which I just thought it's worth mentioning, but I didn't think that it was going to come out in the exam, which I wrote too much, but that's another story. There's the constructive interference, which creates the bright bands where waves reinforce one another, so it's in the middle, and destructive interference, which is created dark bands where the waves cancel out. Can't give you much more details about what those mean, but I'm sure there are other videos on YouTube that could give you a more in-depth understanding of that. So there are two experiments that actually leads to quantum mechanics. So we started off with, okay, is it corpuscular or wave? Young is just like, it's wave. But then we come into this issue of, what we always criticize quantum mechanics about, which is like, well, we can't see it, it's not observation, reality is like observed, what is happening. One thing to take into account is that we're studying things at a molecular level, like super, super small. From my understanding, what is interesting is that we're trying to see how it is that the dynamical laws of like the very, very small, how would it end up being related to statistical laws. There was also like a question of like, if this is the case, then like, classical mechanics, which is statistical or like the bigger picture, is like more fundamental than the very, very small. And you're thinking, how can something very, very big be more fundamental than very, very small? Because usually the small things add up to the big thing. So how do we make up for this, effect that they don't actually align with one another is, I think, one of the biggest debates of quantum mechanics. If I'm wrong, feel free to write it in the comments. Still learning, first class on philosophy of physics, which is really fun. But back to this. So there are two. One is the blackbody radiation problem, and the second is the photoelectric effect. I'm not gonna go too much into this, but I'll just give you the definitions. So a black body is an ideal object that absorbs all light it receives and also emits its own radiation depending on all temperatures. This basically means that if this was true, the intensity of the radiation should increase without limit. However, with experience and the experimental results shows us that the intensity of the radiation of black bodies reaches a certain maximum value and stops. So to resolve this disagreement of experience and wave theory, Planck proposed in 1900s the energy is not emitted continuously but in tiny separate packets. This is how it is that energy is still always emitting, but just not continuously, so that it reaches like a really high level. Because the experiment shows that it stops at a certain point. So how can you resolve the fact that it keeps emitting, but then it stops at a certain point? So he's saying that it doesn't continuously, as in like continuously emits, but it just emits in small energy packets. So it continuously emits, as in it never stops emitting, but these emissions are not continuous, as in they're just sections that are emitted. So energy is not emitted continuously, but in tiny separate packets called quanta. Quanta is the energy of packets that follows the equation E equals hv. Cannot give you the answer for what that means, but now you have the equation. Introduced as a mathematical solution to match experimental results. He did not claim that energy was quantities in nature, but this was the foundation of quantum theory. So quantum is, Marx, chapter 1, volume 1, section 1 of Marx, he talks about quanta. Quanta is just quantities. So I think then we can demystify quantum theory. It's just the fact that it is about quantities. It was the foundation of quantum theory and introduced the particle-like corpuscular view of energy. So the interesting thing here is that he's trying to make sense of how it is that we have a decoherence between theory and experiments, and this led to him actually bringing into light the fact that it also acts as a particle. So the other experiment was the photoelectric effect, the phenomena in which light shining on a surface of a certain metal causes them to release electrons. So according to classical wave theory, increasing the intensity of light should increase the amount of energy delivered. However, the experiment showed that when it's very intense, very bright, it has lower frequencies, so no electrons emitted. However, when it is on high frequency but low intensity, that's when electrons are emitted. So how this was explained by Einstein in 1905 is that he proposed that light behaves like a wave and a particle. So light is made out of small packets of energy called light quanta, photons. So this gives us the concept of wave-particle duality. Light possesses both wave-like, as we see in Young's interference experiment, and particle-like properties, which is quanta, the thing that we learned from black bodies, and the photoelectric effect. So yeah, that is how it is that we had a debate of two sides, and then after that, Young was just like, no, wave, and then they're like, this doesn't coordinate with experiments, so Planck's just like, well, maybe quanta. So then they're like corpuscular, and then they had another experiment, and they were just like, how do we make sense of this? And Einstein is just like, oh, why not both? You know, if you know the tacos girl. So yeah, that is how it is that we arrive at the wave particle theory of light. And I hope to see you in the next one, where I tell you about the 5 stages of how it is that quantum mechanics continually replaced classical mechanics.